Let's look at equilibrium. Equilibrium means your system is balanced, not moving, you know. And if you have something that's not moving, that says the net force has to be 0. Well, if the net force is 0, you can't really break it down to two things. I tried to break it down that all the forces pointing upward, if you add them all, they should equal all the forces pointing down. And all the forces pointing to the right should equal all the forces pointing to the left. That's what that means. You have an equilibrium system. Sum of the force in the x direction is 0. Sum of the force in the y direction is 0. Let's take an example. Before the break, actually, Darren and I were talking about if you take your shoe, I think he was talking about his shoe in the garage, he tied the shoelaces together and dangle that. So the shoelaces will be tied together and there's a nail in the garage here, the shoelace is sitting there, and the shoe is sitting, there's the shoe. Tied, there's the shoelaces. And how much tension on the shoelace there? And is the tension the same? Well, if you look at it, you only got the weight down. And you got the first shoelace pulling upward, and the second one pulling upward. It is the same force. It's the same shoelace. So tension on them is going to be the same. So you will notice if you take all the forces pointing upward, which is twice T there, two of them here, should equal all the force pointing down, which is the weight, that's mass times gravity. So each one of them actually has a tension equals what? Mass times gravity over 2. Yes?
So what if the shoelaces weren't equal length?
Doesn't matter.
It doesn't matter?
Nope.
The tension will be the same?
Nope. Yep. Unless you have an angle on them. So if you have an angle on them, like, I don't know if that's what you meant, but let's say it's this shoe, and you put one shoelace, tied it right there, and you tie another shoelace down here. You have two nails. Now that's a different story. I don't think that's what you meant. Because when you tie them together, even if one side is short, one's long, it's going to be dangled on the top anyway. So it's going to be the same tension. Yeah. But if you attach them like this, like instead of a shoe here, let's say I have a bird feeder here. At home, a lot of people, old people, have these bird feeders. They love to watch birds come in. My mother-in-law does that all the time. So we have one actually string is attached to the house. The other one's attached to a tree, which is big tree like this, the tree. You know, that's why they're not the same height. This is attached to the house here. It's supposed to be a house here, I don't know. And there's the weight of that bird feeder right there. Let's say it's 2 kilograms because there's bird seed in it. And the question, what's the tension? Now, I'm not sure if the tension is the same, so I'll call it T1 and T2. I'm going to prove it's not the same. T2 is horizontal. Doesn't make any angle, 0 degree or 180 if you want to, if you measure with the positive x-axis. And let's say this is 30 degrees. So that's a different example here. So now if we take that force and break it down, that T1 into x and y component, we will have this one. we'll have the weight down, which is mass times gravity. 2 times 9.8 is that 19.6. We get T1 at an angle 30 degrees. And we get T2. These are your forces, your free body diagram. Right there, if you take that spot, you put your axes right here, these are the 3 forces on it. Any force that's not on the x or y axis, you want to break it down to x and y component. So let me take T1, break it down to its components. So this is the weight, 19.6. This is T2. Now I'm going to have a component in this direction, T1 cosine 30, which is 0.87 T1, and T1 sine 30, which is 0.5 T1.
So the rules of physics, you have to break these up, or that's something you do personally?
Well, because you have all the force in the x direction going up equals down, left equals right. So if you have one on an angle, so you got to find the x and y component eventually, so might as well just do it right now. Yeah. So again, that bird feeder is just dangling there. It's not moving. If it's not moving, we have equilibrium. We have a balanced system. If it's balanced, that says if you take all the forces pointing upward, should equal all the forces pointing down. What is pointing upward? Half or 0.5 T1. And what's pointing down? 19.6. Can we get what T1 is? Twice that number. So what is twice that number? 38, 39 point, is it 2? 39.2. Now what about all the forces pointing to the right? Shouldn't they equal all the forces to the left? And what do we have pointing to the right? 0.87 T1 equals T2. 0.87 times 39.2 equals T2 . 34.1, right? Notice the two numbers, are they the same? Is T1, T2 equal? No. So if the angles are not the same, the values will not be equal. I'll take another one, put different angles in it. Every once in a while you look on the news and there's somebody trying to walk from one end of a cliff to another one on a rope, walk the rope with no net. It makes for a good TV, you know. So let's say the rope here, the person was right here, so his weight down. The person was, I don't know, 70 kilogram. The mass was 70 kilogram. And the rope was attached two spots, one to this cliff and the other cliff right here. But the angles, again, the angles are not the same. That's 40-degree angle. Well, that's steep, 40. How about 30? But this is 20. So we took a rope, we attached it to this end, attached it to that end, and this person is going to walk from here to there on that rope. But as you get to the bottom, you know the rope is going to sag a little bit. So he's in the middle there, the rope is sagging, bless you. It makes 20 degrees with this one, 30 degrees with that one. How much tension on each cable? So what's the tension? We'll call them T1 and T2. Because I don't know if they are equal or not. Let the math tell me yes, they are equal or not, or no, they're not equal. So I don't want to take a guess on it. And my weight is what? Mass times gravity? So what's 70 times 9.8? 686. So if I do my free body diagram, that's my free body diagram. If I make this my y-axis right here, and this is my x-axis right there, you can see the three vectors, three forces on it. Now I'm going to take these forces and break them down. Anything not on the x or y axis, I'm going to break it down to x and y component. So here's the weight, which is 686. T1 is going to have a component in this direction and a component in that direction. In this direction, T1 cosine of 30. In this direction, T1 sine of 30. T2. Let's look at T2. To go from here to there, you have to go left and up. So you're going to have a component in this direction and a component up. In this direction, T2, I can write cosine 20. You say, why didn't you use this angle? All that angle gives me the same number, it just gives me a negative value. A negative value tells me which direction? To the left. So I knew it was going to be to the left. So notice if I did, what's cosine? Because this angle will be what? 180 minus 20, which is what? 160. Watch cosine of 160 and cosine of 20. Are they the same value? They are the same value, except one of them is what? Negative. Number-wise, the same thing. So that's why I use the 20, because I know it's going to be in this direction. If I use the 160, it's going to tell me it's negative, which tells me in that direction. And in this direction is what? T2 sine 20. And if you look at sine 20 and sine 160, is the same number. Sine 20, sine 160. So the numbers are the same, it just the minus and plus, it tells me if I use this angle versus that one, I got to do the sign myself. I got to say I got to go to the left, I got to go up. Now that person walking the rope, standing there in the middle of there, is just waiting. Nothing is really moving there, which means we have equilibrium. If you take all the forces, if you add all the forces pointing to the right, should equal all the forces pointing to the left. And what do we have pointing to the right? T1 cosine of 30. And what do we have pointing to the left? T2 cosine what? 20. How many unknowns in that one? 2. T1 and T2. Sum of the forces pointing upward, if you add them all, should equal sum of the forces pointing down. What do we have pointing upward? T1 sine of 30 plus T2 sine 20 equals the weight, which is what? 686. That's my second equation. I have two equations by two unknowns. So how are we going to solve them? So let's see. Let's do that now. Done with the physics, let's jump to the math. We know what cosine of 30, we know what cosine of 20. T1 cosine of 30 is what? 0.87. 0.87 T1 equals, what's cosine of 20? 0.94 T2. Can I solve for T1? You divide by 0.87, 1.08. So that tells me they're not equal. That's from equation 1, from that equation. If you just use your calculator and solve for T1, you end up with that one. I divided both sides by 0.87.
So then you just plug in.
Correct. I'm going to go to this one now. In place of T1, I'm going to put 1.08 T2 sine of 30, right? Plus, so I took T1 out, put 1.08 T2 from here. Plus T2 sine 20 equals 686. .08 times sine of 30, that's half of that, 0.54 T2 plus this times this is 0.54. Sine of 20, 0.34 T2 equals 686. 0.88 T2 equals 686. What's T2 equal to? 686 divided by 0.88. 779.5. 780. Can I find T1? 1.08 times the 780. That's from here. $842. Notice again, it's not the same value. The only time T1 and T2 will be the same when the angles are the same. If you have the same angle, then T1 will equal to T2. But if they're not the same, there's a difference in value. Okay, that was actually equilibrium. Now the next topic is circular motion, when things are spinning in a circle there.